Welcome to this problem walkthrough. In this session, we'll explore problem number 757, set intersection size at least 2. We'll break down the problem, analyze different approaches, and understand the key concepts needed to solve it efficiently. Let's dive right in. The problem requires us to work with a 2D array called intervals, where each subarray represents an interval with a start and an end point. For example, intervals I equals start underscore I, end underscore I, represents an interval that begins at start underscore I and ends at end underscore I. The goal is to find the smallest possible set of integers such that every interval in the input contains at least two distinct integers from this set. This means that for each interval, start underscore I, end underscore I, we need to choose two integers x and y such that both x and y lie within that interval, and x is not equal to y. Once we determine this minimum set of integers, the output will be the size of the set. For the first example, we are given the input intervals equals 1, 3, 1, 4, 2, 5, 3, 5. The output is 3, which means the minimum set of integers required to satisfy the condition has 3 elements. One possible solution is the set 2, 3, 4. Let's see why this works. For the first interval, 1, 3, the integers 2 and 3 are within the interval. For the second interval, 1, 4, the integers 2 and 3 are also within the interval. For the third interval, 2, 5, the integers 2 and 3 satisfy the condition. Finally, for the fourth interval, 3, 5, the integers 3 and 4 are valid. As all intervals are covered, the minimum set size is 3. Now, consider the second example with the input intervals equals 1, 2, 2, 3, 2, 4, 4, 5. This time, the output is 5, meaning the minimum set of integers has 5 elements. One possible solution is the set 1, 2, 3, 4, 5. Let's verify. For the interval 1, 2, the integers 1 and 2 are valid. 4, 2, 3, the integers 2 and 3 work. For 2, 4, the integers 2 and 3 also satisfy the condition. Finally, 4, 4, 5, the integers 4 and 5 are valid. Since all intervals are covered, and no smaller set can meet the requirements, the answer is 5. To handle edge cases, consider situations like a single interval, such as 1, 2. In this case, the output must include exactly 2 integers from the interval, even if it's the smallest possible range. Another scenario is when all intervals overlap significantly, for example, 1, 10, 2, 9, 3, 8. Here, the solution must minimize the set size efficiently while ensuring each interval contains at least 2 integers. Additionally, for very large intervals like 1, 10 to the power of 8, 2, 10 to the power of 8, the algorithm must remain efficient and not exceed the time complexity limits, ensuring scalability even for the upper bounds of the constraints. When tackling this problem, one initial approach we might consider is the brute force method. The intuition behind this is straightforward. For each interval, we generate all possible subsets of integers and check if each subset covers at least 2 integers from every interval. While this guarantees correctness, it's computationally expensive because generating subsets and verifying the conditions involves exponential time complexity. This makes it impractical for larger inputs, such as when intervals span a wide range. Alternatively, we have the greedy approach, which is a more efficient and scalable solution. The key idea here is to sort the intervals by their ending points. By processing intervals in this order, we can carefully choose integers that are as close as possible to the end of each interval. This minimizes overlap between the intervals and reduces the size of the set we select. Two important observations make this approach effective. First, every interval needs at least 2 integers to satisfy the problem's condition, and second, choosing integers close to the interval's endpoint ensures minimal interference with future intervals. Sorting by the endpoints is what allows this strategy to work seamlessly. To implement the greedy approach, we follow a structured set of steps. First, we sort all the intervals by their endpoints. Then, for each interval, we maintain a set of 2 integers to ensure the interval is covered. If the current interval does not overlap with the integers selected from the previous interval, we simply choose the 2 largest integers within the current interval. However, if there is overlap, we adjust our selection to ensure there are still at least 2 integers while avoiding redundant selections. Throughout this process, we keep track of all selected integers to ensure that every interval is properly covered. The efficiency of this approach comes from the fact that sorting the intervals takes O, n log n, where n is the number of intervals, and processing them linearly takes O, n. Together, this results in an overall time complexity of O, n log n. This balance of efficiency and correctness makes the greedy approach a compelling choice. Unlike the brute force method, which is computationally infeasible, this approach is optimal for larger inputs and adheres to the constraints of the problem. While a dynamic programming approach is another possible solution, it introduces unnecessary complexity. In this method, we would track a state, such as dp I, representing the minimum set size needed to cover the first I intervals. However, calculating state transitions would involve exploring multiple subset combinations for each interval, leading to significant overhead. Given this, the greedy approach stands out as the better solution. It is simpler, more intuitive, and faster, avoiding the need for additional state management. By sorting the intervals and processing them sequentially, we minimize the size of the set while guaranteeing that all intervals are covered. This strategy strikes an ideal balance between clarity, performance, and correctness. Compared to brute force, it's exponentially faster, and compared to dynamic programming, it avoids unnecessary complexity. Adopting the greedy approach ensures that we solve the problem in the most efficient and straightforward manner, making it the optimal choice for this scenario. The problem we're tackling involves a set of intervals, and the goal is to determine the smallest subset of integers such that each interval has at least two integers from this subset within its range. For example, if the intervals are 1, 3, 2, 5, we need to find a subset of integers that satisfies this condition for both intervals. To start, let's consider the brute force approach. First, we determine the range of integers we need to work with, which is derived from the minimum start and maximum end values among the intervals. In our example, the range is 1, 5. Next, we generate all possible subsets of integers within this range. Since there are 2 n subsets for a range of size n, this can grow very quickly as the range increases. Once we have all subsets, we evaluate each one to check if it satisfies the condition of covering at least 2 integers for every interval. For each interval, start to end, we count how many integers from the subset fall within this range. If the count is less than 2 for any interval, that subset is invalid. If all intervals are satisfied, we mark the subset as a valid candidate. While this approach is conceptually simple, it's computationally expensive due to the exponential growth of subsets as the range increases. After identifying all valid subsets, the final step in the brute force approach is to compare them and find the one with the smallest size. If there are ties, we can choose the lexicographically smallest subset to ensure consistency. However, given the inefficiency of generating and evaluating all subsets, we need a more practical solution. This is where the greedy algorithm comes into play. The first step in the greedy approach is to sort the intervals based on their endpoints. Sorting allows us to process the intervals in an organized manner and ensures that intervals finishing earlier are handled first. Once sorted, we initialize an empty result set to store the integers we choose. Then, as we iterate through each interval, we check whether the result set already has at least 2 integers within the interval range. If not, we add the largest 2 uncovered integers from the interval to the result set. By prioritizing the largest integers, we maximize the likelihood that these choices will also satisfy future intervals. This process continues until all intervals have been processed, ensuring that every interval is covered by at least 2 integers. The greedy algorithm relies on a few key insights to work efficiently. First, the greedy choice property ensures that making locally optimal decisions, like choosing integers for the current interval, leads to a globally optimal solution. Sorting intervals by their endpoints is crucial here, as it allows us to address intervals systematically. Second, by focusing on adding the largest uncovered integers within an interval, we reduce the risk of missing coverage for overlapping intervals. This approach ensures that our choices not only satisfy the current interval but also potentially help with subsequent intervals. Finally, the efficiency of the greedy algorithm stands out. Unlike the brute force method, which requires generating and evaluating all possible subsets, a process with O(2 to the power of n) complexity, the greedy approach sorts the intervals in O, k log k, and processes them sequentially in O, k, where k is the number of intervals. This significantly reduces the computational effort, making the greedy algorithm far more practical for larger inputs. To implement the greedy algorithm, we rely on a few key data structures. First, a result set or list is used to store the chosen integers. This data structure allows for efficient membership checks and additions. Second, the intervals array is sorted by endpoints to facilitate the greedy processing. This sorting step ensures that intervals are handled in the correct order, which is critical for the algorithm's correctness. Additionally, it's important to handle edge cases carefully. For non-overlapping intervals, the greedy approach processes each interval independently, ensuring that each gets the required coverage. Completely overlapping intervals are also managed effectively, as the algorithm guarantees that the overlapping region will be covered by at least two integers. When there's only a single interval, the solution is straightforward: simply select the two largest integers within that interval. Finally, intervals with very small ranges, like 3, 3, require special handling to ensure that no invalid subsets are selected. By addressing these edge cases, the algorithm remains robust and reliable. To see the greedy algorithm in action, let's walk through an example. Suppose the input intervals are 1, 4, 2, 6, 8, 10. First, we sort the intervals by their endpoints, but in this case, they're already sorted. Starting with the interval 1, 4, we add the largest two integers within the range, which are 3 and 4. These integers are added to the result set. Next, we process the interval 2, 6. Since the integers 3 and 4 already cover this interval, no additional integers are needed. Finally, for the interval 8, 10, we add the largest two integers within the range, which are 9 and 10. These integers are added to the result set as well. At the end of this process, the result set contains 3, 4, 9, 10. This subset satisfies the condition of covering at least two integers for each interval, making it the optimal solution. The greedy algorithm provides an efficient and effective solution to the problem. By sorting intervals and processing them sequentially, the algorithm ensures correctness while minimizing computational effort. It achieves this by focusing on adding the largest uncovered integers within each interval, which balances local and global optimality. This approach not only reduces the complexity compared to the brute force method but also guarantees that the solution satisfies all constraints. Overall, the greedy algorithm is a powerful tool for solving this type of interval coverage problem, demonstrating the importance of strategic decision-making in algorithm design. This solution implements a greedy algorithm to solve the problem: set intersection size at least 2. The goal is to ensure that every interval in the given list has at least two integers in the result set. First, the intervals are sorted by their ending points to prioritize covering intervals that finish earlier. In case of ties, intervals are sorted by their starting points in descending order. This ensures a well-defined order for processing intervals. Next, we maintain a list to underscore cover that tracks the integers in the result set. For each interval, we count how many integers from the last two elements of to underscore cover fall within the interval. If fewer than two integers from to underscore cover cover the interval, additional integers are added starting from the interval's endpoint and moving backward. This ensures minimal additions to the result set while satisfying the problem's constraints. Finally, the length of to underscore cover is returned as the size of the smallest set that satisfies the given conditions. The algorithm is efficient due to the sorting step and the linear traversal of the intervals, making it suitable for large inputs. Here, we begin implementing the solution in Java. First, we import the necessary libraries and define the main method inside the solution class. The goal is to determine the minimum size of a set such that at least two integers from it intersect with every interval in the given list. To start, we sort the intervals by their endpoints in ascending order. If two intervals have the same endpoint, we use their start points in descending order as the secondary sorting criterion. This sorting ensures that we can process the intervals in a way that minimizes the number of elements added to our result set. Next, we initialize a list called toCover to track the last two elements that will cover the intervals. Then, we iterate through each interval in the sorted list. For every interval, we extract its start and end points. We check how many of the last two elements in toCover already fall within the current interval. This is done by iterating over the last two elements of the list, ensuring they lie between the start and end of the interval. Based on this count, we determine if additional elements need to be added to cover to satisfy the condition of having at least two intersecting integers for the current interval. If fewer than two elements are found, we add the necessary numbers, starting from the interval's endpoint and moving backward by one step for each required number. Finally, after processing all intervals, we return the size of the to-cover list, which represents the minimum set size that satisfies the problem's conditions. This approach ensures that we always maintain at least two integers in the set to cover each interval, while keeping the overall size of the set as small as possible. By iterating through the intervals in their sorted order and carefully managing the set's contents, we achieve an efficient and optimal solution to the problem. This completes the implementation of the method. To solve this problem, we start with an example input where the intervals are 1, 3, 1, 4, 2, 5, 3, 5. The first step is to sort these intervals by their end values. If two intervals have the same end value, we sort them by their start values. After sorting, the intervals become 1, 3, 1, 4, 3, 5, 2, 5. Next, we initialize an empty list called to_cover, which will store the elements we choose to ensure that each interval has at least two elements covered. For the first interval, 1, 3, we check how many elements in to_cover already cover it. Since to_cover is empty, no elements cover this interval, so we add two elements. Starting from the end of the interval and going backward, we add 3 and 2 to to_cover. Now, to_cover contains 2, 3. For the next interval, 1, 4, we check how many elements in to_cover already cover it. Both 2 and 3 are within the interval, so it is fully covered with a count of 2. Therefore, we don't need to add any new elements, and to_cover remains 2, 3. For the interval 3, 5, we see that only the element 3 in to_cover falls within this interval, so the count is 1. Since we need at least two elements, we add one more element, which is 5, to to_cover. Now, to_cover becomes 2, 3, 5. Finally, for the interval 2, 5, both 3 and 5 from to_cover are within the range, so the count is 2, and the interval is fully covered. No additional elements need to be added, and to_cover stays 2, 3, 5. At the end of processing all intervals in this example, the to_cover list contains 3 elements, 2, 3, and 5. The length of to_cover gives the final output, which is 3. Moving to another example, we now consider a case with overlapping intervals 1, 2, 2, 3, 3, 4, 4, 5. These intervals are already sorted by their end values, so no additional sorting is needed. We proceed to initialize to_cover as an empty list. For the first interval, 1, 2, no elements in to_cover cover it, so the count is 0. We add two elements, 2 and 1, starting from the end and moving backward. Now, to_cover is 1, 2. For the interval 2, 3, only the element 2 from to_cover falls within this range, so the count is 1. To ensure two elements cover this interval, we add 3 to to_cover, which becomes 1, 2, 3. Next, for the interval 3, 4, only the element 3 covers it, so the count is again 1. We add 4 to to_cover, resulting in 1, 2, 3, 4. Finally, for the interval 4, 5, the only element from to_cover that covers it is 4, so the count is 1. To meet the requirement of two elements, we add 5 to to_cover. Now, to_cover becomes 1, 2, 3, 4, 5. After processing all intervals, the length of to_cover gives the output, which is 5. Lastly, let's look at a simple case with just one interval, 10, 20. In this single interval example, no sorting is needed since there's only one interval. We initialize to_cover as an empty list. For the interval 10, 20, no elements in to_cover cover it, so the count is 0. We add two elements, starting from the end of the interval and moving backward. This means we add 20 and 19 to to_cover. Now, to_cover contains 19, 20. Since there are no more intervals to process, the length of to_cover gives the final output, which is 2. To analyze the time complexity of our solution, let's first consider the sorting step. We use the sort method to arrange the intervals by their endpoints, and secondarily by their start points. Sorting a list of n intervals requires n*log n time. Next, we have the iteration step. Here, we loop through each of the n intervals, and within each iteration, we check the last two elements in the to_cover list. This check is a constant time operation, O1, as it involves only a fixed number of elements. Additionally, at most two new elements are appended to to_cover for each interval, which is also O1 per interval. Combining these operations, the work done during the iteration step is O1 per interval, resulting in O(n) for all intervals. So, the total time complexity combines the sorting step, O(n*log n) and the iteration step, O(n). When we sum up the contributions to time complexity, the sorting step, which takes O(n*log n), dominates over the iteration step, which is O(n). Therefore, the overall time complexity of the solution is O(n*log n). Now, let's discuss the space complexity. First, the input list intervals occupies O(n) space, as there are n intervals to store. Then, we have the to_cover list, which stores the elements selected to ensure every interval is covered. In the worst case, where each interval contributes two elements, to_cover could contain at most two n elements, making its space usage O(n). Lastly, the algorithm does not use any extra data structures or recursive calls, so the auxiliary space usage is O(1). Adding these together, the total space complexity is determined by the input storage and to_cover, giving us O(n). The total space complexity therefore simplifies to O(n). Now, let's analyze the algorithm's behavior across different scenarios. In the best case, where all intervals are highly overlapping, fewer elements need to be added to to_cover. However, since the sorting step is still required, the best case time complexity remains O(n*log n). On average, a moderate number of elements are added for each interval, but the sorting step still dominates, resulting in an average case time complexity of O(n*log n). In the worst case, where intervals are disjoint or overlap minimally, two elements are added for each interval. Even in this scenario, the sorting step remains the dominant factor, keeping the worst case time complexity at O(n*log n). Thus, across all cases, the time complexity is consistently O(n*log n). To understand the efficiency of this approach, let's compare it to a naive solution. A brute force method might involve checking all pairs of intervals to ensure coverage. This would result in a time complexity of O(n², as each interval would be compared with every other interval. In contrast, our optimized solution achieves O(n*log n) time complexity by sorting the intervals and using a greedy approach with the to_cover list. This is a significant improvement, especially for large n, as sorting is much faster than quadratic operations. Mathematically, O(n*log n dominates O(n) because the growth rate of n*log n outpaces n as the input size increases. Spacewise, the solution is efficient as well, with a linear space complexity of O(n), determined mainly by the to_cover list and the input storage. This combination of O(n*log n time and O(n) space complexity makes the algorithm highly scalable and suitable for handling large inputs efficiently. One key mistake is not accounting for overlapping intervals. Overlaps can have a significant impact on the solution, especially when intervals share large portions of their range. For example, given intervals like 1, 5, and 4, 8, treating them independently might result in missing critical elements that are necessary to satisfy the condition. Another common issue is inefficient subset generation. When solving this problem, generating all subsets can lead to exponential time complexity, which is computationally expensive and likely to result in time limit errors. To address this, we can use greedy or dynamic programming approaches to narrow down the solution space effectively. It's also critical to keep edge cases in mind. Scenarios like single intervals, fully nested intervals, or completely disjoint intervals often introduce bugs. Testing with boundary cases, such as an empty input or intervals with extreme values, is essential to ensure correctness. Lastly, misunderstanding the requirement to cover at least two integers for each interval can lead to solutions that only partially meet the condition. To avoid this, carefully track the range covered by each interval during implementation. Another mistake to watch for is assuming that the input intervals are pre-sorted. If the intervals are unsorted, algorithms relying on sorted input will produce incorrect results. To fix this, always make it a habit to explicitly sort the intervals during pre-processing. Now, in terms of interview strategies, pattern recognition is crucial. Problems like this often involve interval manipulation, which is a recurring theme in greedy algorithms, dynamic programming, or sorting-based problems. Recognizing when to optimize coverage or subset selection is a key skill. Additionally, understanding the trade-offs between different approaches is important. Greedy algorithms are faster and simpler to implement, but they may fail for certain edge cases. Dynamic programming, on the other hand, is more robust but can be harder to debug, especially under time pressure. When explaining your approach to an interviewer, focus on clarity. Justify why you chose a particular method, especially if you skipped brute force. If time permits, discuss possible optimizations and weigh their trade-offs. For instance, sorting intervals first can simplify the subset selection process and improve performance. To deepen your understanding, there are some closely related problems worth exploring. The first is problem 1288, remove covered intervals, which focuses on identifying and removing redundant intervals. Next is problem 56, merge intervals, a fundamental problem that teaches core interval manipulation techniques. Another related problem is problem 986, interval list intersections, which emphasizes merging and intersecting intervals. Finally, problem 435, non-overlapping intervals, challenges you to select intervals strategically to minimize overlap. Moving on to alternative approaches, a common and effective method is the greedy approach. Here, intervals are sorted by their start or end points, and elements are iteratively selected to maximize coverage. This method is simple and efficient for many cases, but it may struggle with specific configurations or edge cases. Dynamic programming is another option. By tracking the state of coverage for subsets of intervals, DP provides a robust solution that handles edge cases well. However, it comes with higher complexity and can be more challenging to implement, particularly under time constraints. For more comprehensive solutions, backtracking is an option. In this method, subsets are explored recursively, and coverage conditions are verified at each step. While backtracking guarantees accuracy, it is computationally expensive and impractical for large inputs due to its exponential time complexity. Another interesting approach is bitmasking, where subsets are represented as bitmasks. This allows for efficient manipulation and evaluation of subsets. Bitmasking offers a compact representation and speeds up subset operations, but its scalability is limited. The exponential growth of the subset space makes it unsuitable for problems with a large number of intervals. Each of these approaches has its strengths and weaknesses, and the choice depends on the specific constraints and requirements of the problem. By understanding these techniques and their trade-offs, you can build a flexible problem-solving toolkit for interval-based challenges. Great job following along. To summarize, we tackled problem number 757 using a combination of sorting and greedy techniques, achieving an efficient solution. Remember, interval-based problems often benefit from these strategies. Thank you for watching, and don't forget to like, share, and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!